Recording. All right, you guys. So we left off with Unit 2. We were doing drawings of covalent Lewis dot structures and looking at hybridization and molecular geometries based on their Lewis dot diagrams. But the next piece of understanding properties of substances is understanding whether or not something is polar or nonpolar, which of course is going to depend on two things. It's going to depend on the polarity of the bonds, like is the bond polar or nonpolar? And then secondarily, it's going to depend on the molecular geometry. So let's first talk about bond polarity. The reason why a bond would be polar is because of differences in electronegativity values. So I think like one of the example problems on that AP Classroom practice that you guys did was like, is a nitrogen-nitrogen bond polar or nonpolar? And you guys all correctly answered that and said that that was a nonpolar bond because, you know, nitrogen has an electronegativity value of around 3.0. And so that's a measure of love for the electrons in that bond. So if they both love and pull on those electrons the same amount, that bond is nonpolar. The electrons are going to be equally distributed throughout that bond. No one's going to end up partially positive or partially negative. But what if we had, let's say we had different elements. Let's say we had hydrogen bonded to chlorine. Hydrogen's electronegativity value is like 2.1. And chlorine's is like 3. I can't read that small. I don't know. Let's say 3.3. This is a measure of love for electrons or attraction for electrons in that shared bond. So those electrons are going to be pulled more towards chlorine, which is going to make your chlorine partially negative and your hydrogen partially positive. So that is a polar bond when you've got differences in electronegativity. And of course, you guys, your trend is electronegativity increases up and across. So like fluorine being your most electronegative atom on the periodic table. No electronegativity values for your noble gases because they don't bond. Any questions there on bond polarity? Okay. All right. So here's the funky thing, is that even if you have a polar bond, sometimes your molecule overall will be nonpolar. Okay, so molecular polarity is what the molecule as a whole is feeling in terms of partial charge. And so there are times when bond polarity can cancel out. If the shape is symmetrical. And in addition to being symmetrical, and all terminal atoms are the same or have the same electronegativity values. All terminal atoms have same E negative. So here's an example of that. Like in the carbon dioxide molecule, which we know is linear, you have polar bonds there, right? Oxygen is more electronegative than carbon. So like that bond is polar and pulling towards the oxygen. And this bond is polar, pulling towards the oxygen. But if I were to add up those two vectors, if I were to sum up those two vectors together, they would cancel out. So this is an example of a molecule that has polar bonds, but a non-polar molecule overall. Savannah's spaghetti marshmallow structures. broken and sad, and she's throwing it in the trash.
No.
Goodbye, spaghetti tower. Okay. Savannah, science is failure, you know? This is you fail 9 times out of 10. I know. What a bummer. Okay. So let's talk about the shapes that are symmetrical, you guys, right? So the symmetrical shapes where this could happen, where all of your terminal atoms end up in a canceling out of bond polarity, would be linear, that's symmetrical, trigonal planar. And when I'm talking linear, I'm talking 3-atom linear. Like this example, this HCl example, that 2-atom linear, that obviously doesn't have a vector to cancel with. So 3-atom linear, trigonal planar, tetrahedral. It's really the heads of all of the families, right? So the 3 domains, 4 domains, trigonal bipyramidal, 5 domains, and octahedral, 6 domains. So when you've got those equivalent domains in your geometries and none of them are lone pairs, like if they're all bonded, then you've got symmetrical shapes and symmetrical arrangements. But if you have something like, instead of tetrahedral, let's say you have like, let's say you have pyramidal, right? Like you have NH3. Here's an example of a non-symmetrical shape. So here, all of these polarity arrows are going up towards that lone pair. You're going to end up with a really partial negative up here, and this bottom portion of the molecule where all the hydrogens are, that's going to be partially positive. So here's an example of where polarity does not cancel. This is going to be a polar molecule. Now, in order to be polar, you have to have polar bonds, right? So like if you have non-polar bonds, it doesn't matter what the shape is, it's always non-polar. Any questions on bond polarity versus molecular polarity? Okay, so the reason why we care if molecules are polar or non-polar is because, obviously, those determine our intermolecular forces. And there are 3 main types of IMFs. Now remember, when we're talking about IMFs, we are talking about the forces at play in covalent molecules. Okay, so this is for covalent only. If you're talking about something that's ionic, it's that crystal lattice structure that's going to determine properties. If you're talking about metallic, it's that sea of electrons. If you're talking about a covalent network solid, then you're talking about the covalent bonds between the molecules themselves. But we're just talking about plain old covalent, or another word for covalent, molecular compounds. And let's just review this chart right here. Don't go to the other information yet, because I don't love this chart for that. But let's look at the definitions. Okay, so a dispersion force happens in all atoms and molecules, even if they're polar. They will also, on top of their dipole-dipole, they will all experience some dispersion force as well. And in order to get these partial areas of partial positive and partial negative, those would not just naturally be there between 2 hydrogens. Like they would have to sort of come close together. And so we have a temporary dipole, okay, instantaneous or temporary. Meaning when these 2 things are close together, the electrons over here are going to shift and make this side of the molecule a little bit more negative and bigger, and this side of the molecule a little bit more negative and bigger. They used darker color here to show where the electrons are shifting to, okay? And so you end up with this partial negative, and it can attract to the partial positive for a moment in time. But this is our weakest IMF because it's a temporary situation caused by these 2 molecules being near to one another for that moment in time. These are these diagrams that I can never draw, and you guys always laugh at me. Bloop. Okay. Now, we can increase the strength of a dispersion force, okay? And so this is correct. An increase in strength as molar mass increases, because with an increase in molar mass, you get an increase in the number of electrons. And this is my favorite word. Everybody loves this word. You get an increase in the polarizability of that molecule, the squishy squashiness of the electron cloud. More electrons moving around, bigger partial negative, bigger partial positive. Any questions on dispersion? Slightly stronger would be a dipole-dipole when you have this permanent area of positive and negative charge. So like there's going to be a permanent attraction here between the hydrogen in one of these. So like here's our dispersion force, our dipole-dipole force, and the hydrogen in the other molecule. So this is not an all molecule situation. This is a polar molecule only situation because these dipoles are permanent. They are not temporary. They are not caused by these molecules coming close to one another. They are already polar molecules. And so that strength is a little bit stronger. Now, this particular chart says they are stronger when the molecules are closer together. I mean, that's true, obviously, for all any charged situation. When the distance between the charges is lesser, you're going to have a stronger attraction. So yes, this is true, but I also want you guys to recognize that these also get stronger when there is an increase. I don't know, I'm writing an increase arrow and the word bigger. When there is an increase in what we call the dipole moment. And that's just a measure of like the magnitude of the charges on the positive and the negative. So like if you have a bigger positive and a bigger negative, you have a stronger partial charge or a stronger dipole moment. And like, why would something have a stronger dipole moment? When you have a bigger difference in electronegativity values. So for example, we were looking at the difference in electronegativity between hydrogen and chlorine. You know, it was a difference of around like 1. But what if we were looking at hydrogen to fluorine? So we said hydrogen was 2.1, and I think fluorine is like 4.0 or something. It's huge. This difference in electronegativity is much greater. So like that's gonna make my negative dipole on fluorine a lot greater and my positive dipole on hydrogen a lot greater than they were here in the hydrogen to chlorine. So you can think of this as like a super beefed up, like strongest of the dipole dipoles. And those we call hydrogen bonds. So when you have a hydrogen bonded to nitrogen, oxygen, or fluorine, really electronegative, very electronegative elements, that makes these dipoles so big that their attraction to a neighboring molecule with that same sort of situation happening, it makes that attraction like super duper strong. And so my hydrogen bond would be like this pink dotted line here. That's the hydrogen bond. And these are our strongest IMFs. And the other information here is it's not chemical bonding. Like we're not talking about the bond between the hydrogen and the fluorine. We're talking about the intermolecular attraction between the fluorine on one and the hydrogen on the other. Any questions on those IMFs? Okay, I'll just keep talking into the void. Properties dependent on IMF strength. Okay, so when you have whoa, I did not want yellow, sorry. I wanted blue. When you have a strong IMF, that means that those molecules are being held together tightly. So a strong IMF will result in a high melting point. Who's clicking away over there? A high melting point and a high boiling point, right? Because it would be really hard to melt and to boil. How do I, there we go. Yes. Okay, so you have a really high melting point and a high boiling point when you have strong IMFs. Ooh, this is Austin's favorite. When you have strong IMFs, you are going to
volatility.
Yes. You're going to have very low vapor pressure. Not volatility, Austin. We don't measure. We don't
It's the
measure.
same thing.
We're going to have low vapor pressures. Remember, you guys, vapor pressures are the pressure exerted by the gas phase of a substance above its liquid phase. So if we have a strong IMF keeping it in the liquid phase, we're not going to get a lot of particles up there, and we're going to get low vapor pressure. Substances that have low vapor pressure are called non-volatile substances. Non-volatile, low vapor pressure, meaning they do not easily become a gas. And if we want to use the word volatile, that's referring to something. See, these, Austin, these are adjectives, not nouns.
It's the same thing.
Volatile substances have high vapor pressures because they readily or very easily become a gas. Okay. I feel like there's more properties that I should be discussing here.
Mr. Rare,
Yeah.
wouldn't it be a low melting point?
No. Austin. Would it be a low melting point? No, high melting point. Because if it's being held together really strongly in the solid state, you would need a lot of heat. With a strong IMF, you need a lot of heat to
I was
separate
talking
it.
about freezing point, sorry.
Oh, there you go. Well, melting point and freezing point are the same, though. They're the same temperature.
Okay, yeah.
The temperature at which
So
something...
there's a low freezing point, right? Low freezing point, right?
No.
High?
High. So think about it. If something's in the liquid state and you want it to freeze, right? If it has a strong attraction to the like if the particles are strongly attracted to each other, they're going to come together from a liquid to a solid very easily. And you would not need to take away a lot of heat. You would not need to drop the freezing point super low in order for that to occur.
Okay.
Right? So melting point and freezing point are the same point, like temperature point on a heating curve. It's just a matter of which direction you're talking about going. Are you talking about going solid to liquid or liquid to solid?
Okay.
Okay. I think Jack, when we look at the heating curve, that'll help make a little bit more sense.
Okay, thank you.
Okay. Yeah, sure. Okay. Vapor pressure. I talked about vapor pressure. I talked about melting point and boiling point. I don't know. Theo will tell me if I forgot something. Okay. Moving on. Oh, Austin. Austin, you're going to have to erase your same. Bye-bye. Okay. Let's now look at, maybe we should talk about those. Maybe we should talk about that heating curve. Yeah, let's talk about states of matter and the heating curve, and then we'll talk separation techniques. Okay, so if you are talking about one particular substance, like let's say we're talking about water, we know that at room temperature, at 25 degrees Celsius, water is a liquid. And of course, we can add heat and turn this into water vapor. And we can remove heat and turn it into a solid. So these phase changes can depend on temperature, but they can also depend on pressure. And I think I showed this to you guys, like where I took water and we put it into the vacuum pump and we removed pressure and we saw it boil at room temperature. So don't forget that these states of matter can depend on temperature and they can depend on pressure, okay? Now, besides temperature and pressure determining states of matter, also what determines states of matter are IMFs, or the forces that are just holding together substances in the first place. So for example, ionic compounds tend to always be solid. Like, why is it that ionic compounds are solid? Well, because they have a crystal lattice structure, and that is a very strong structure. So at room temperature, your ionic compounds will be solids, and they take a ton of heat to melt them or to boil them. Metals also tend to be solids. So your sea of electrons will also tend to be a solid at room temperature. What else is a solid at room temperature? Oh, your covalent network solids that we talked about last time. The covalent network solids, like diamond and graphite, that's a very, very strong intermolecular force. And so that will usually result in a solid at room temperature. And then there are also some molecular solids. For example, like iodine, I2. Iodine is a solid at room temperature. The reason for that is even though its IMF is only a dispersion force, which you think is a weak IMF, this dispersion force, iodine, is a very massive molecule. It has a big molar mass, which means it has lots of electrons and is very polarizable. So this dispersion force in iodine is very strong and leads iodine to be a solid at room temperature. So things that are weaker, things that have weaker IMFs will be liquid at room temperature, and even weaker IMFs will be gaseous at room temperature. So you think about like what are some things that are gases at room temperature? Obviously, just some of our elemental gases like oxygen or carbon dioxide, which is a nonpolar molecule. So, you know, these are if something is a gas at room temperature, it's got very weak IMFs. And if something is a solid at room temperature, it's got stronger IMFs. Okay, so be thinking about all of the factors that play a role in states of matter. And we can look at changes in state in two different ways. We can look at it in terms of just temperature change. And when we do that, we're going to look at this graph over here on the right, and these are called heating curves. Okay, so this heating curve is showing us an increase in temperature over the course of time. So if this was the heating curve for water, in order for water to be in the solid state, we would have to be below 0 degrees Celsius. So like maybe let's say we started this experiment out at like -10 degrees Celsius. We're gonna add heat, add heat, add heat, add heat. Those solid particles are gonna vibrate faster and faster and faster and faster until we get to an average kinetic energy that results in a temperature of 0 degrees Celsius. This point right here, where we're still adding heat, but the temperature is not changing, this is your phase change. This is where the melting is occurring. And once all of the solid ice has melted into liquid water, then the temperature will start to rise again. The liquid particles will move faster and faster and faster and faster and faster and faster, and temperature will increase, 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 all the way to 100 degrees Celsius, where all of a sudden that curve is going to flatten out again. Because this is where the liquid water turns into water vapor. This is where it boils. Vaporization. Oops, it's an ugly circle. Okay. And then up here is where it's a gas. So if I was doing this in reverse, like if I was taking away heat and I was going from the gaseous state to the liquid state, we wouldn't call this vaporization, we would call it condensation. So this is what I was talking about these being at the same temperature, Jack. So like if you have a gas and you're cooling it, then it's going to condense into a liquid. And you take that liquid water and you put it in an ice tray in your freezer and you take away temperature, take away temperature, take away temperature. And all of a sudden you get to 0 and it's going to start to freeze. So it just depends on your direction in which you're traveling. Vaporization is going this way, condensation is going that way. Melting's going this way, freezing's going that way. So these circled portions, you guys, are your phase change, where you would take into account the delta H of fusion and the delta H of vaporization. And these rises in the graph, where the substance is heating up, if we wanted to calculate how much heat was required to get to those phase changes, we would do Q equals MC delta T calculations. So remember, we did a problem where we like calculated the total amount of heat required to take a solid chunk of ice and turn it into water vapor. You'd have to like add up all of those. I'm not going to spend time going over one of those problems, but if you want to review it, there's definitely an example, blue example problem in your textbook. But this graph, you guys, only looks at how temperature affects state of matter. There's another type of graph called a phase diagram. Okay, so did I label these? Yeah, so this is my heating curve. And a phase diagram takes into account, where's my phase diagram? Ah, down here. A phase diagram takes into account pressure and temperature. So if you're thinking about what you know, right, at low temperatures, so those molecules are not moving very fast, and high pressures, meaning they're pushed close together, that's going to be a solid, right? So if we look at these like low temperature range, high pressure range, that's where my substance is going to be a solid. And if you take a solid and you add heat, you can turn it into a liquid. And if you take a liquid and you add heat, well, it depends on where you are on this point, but if you take a liquid and you add heat, you can also turn a liquid into a gas. Or if you wanted to change state without changing temperature at all, see how I could go from the liquid state to the gaseous state just by reducing pressure? Even at the same temperature, that's what I did in the lab. Like we had that big vacuum pump, you know, that big bell jar thing. This was my bell jar, and this was like my beaker of water. And I pulled all of the gas out from underneath here with my vacuum pump. So I reduced pressure. And when I reduced this pressure up above the liquid was able to turn into a gas because it wasn't being pushed on by the atmospheric pressure anymore. So these types of diagrams, these phase diagrams, show you at what temperatures and pressures the state of matter is determined by. And two important points on these graphs. One is the triple point. That's the point where it is a solid, a liquid, and a gas all at the same time. So there are temperatures and pressures at which we can get all three phases to exist. And then this critical point out here is this point where there's sort of like no difference between the liquid phase and the gas phase. Like you can't tell the difference between them anymore. And that's where we watched the video of that cute little old man British scientist and his demonstration of a supercritical fluid out here. Supercritical fluid, where you've got very dense, essentially a very dense gas. So phase diagrams and heating curves, two different ways to look at states of matter. Or changes in state, I should say. Okay, doing good. I hope you guys are awake. I can't see your faces. Now, where did I want to go? I think I wanted to talk about separation techniques. Yes, two types of separation techniques depending on IMFs, okay? This first type, and you guys did some beautiful art with this, the first type of separation technique we're going to talk about is chromatography. Chroma, meaning color, chromatography, graphy being to write, so to write with color. And in chromatography, you remember from honors chem, we separated like all of the different colors of dyes and M&Ms, you know, the different food dyes. You can separate dyes in inks, you can separate food dyes, you can separate DNA, you can separate all kinds of things based on their intermolecular attractions. So if we were to do some like measured chromatography, you guys didn't measure anything yesterday on your coffee filters or today on your coffee filters, but you saw that some colors of dye traveled farther than others. So when we do chromatography, this original place where we spot our dye, this is called the origin. So like, let's say you put some black marker on your origin, and then you submerged that in a solvent, okay? The solvent, you guys, is called your mobile phase, because that's the thing that can move. This is your mobile phase of your chromatograph. And that solvent is going to move up your paper, and it's going to carry with it the different components of the mixture. So like maybe you saw some red dye. Oh, that's green, Amanda. Maybe you saw some green dye spot out there, and then you saw some red dye spot out there, and the last spot you saw was blue. So like you know that your black dye was actually composed of a mixture of green and red and blue inks. The things that travel the farthest have a greater attraction to the solvent. Okay, so they have a strong solvent attraction because they traveled farther with the solvent. So like, let's say the solvent was water. I would suspect that this blue colored dye had a lot of hydrogen bonds in it because it stayed with the water the longest. This green color dye, on the other hand, had a stronger attraction to the paper. Strong, what we call stationary phase attraction. The paper is your stationary phase. So if the paper is nonpolar, I would expect that this green dye is nonpolar, and or more nonpolar than the blue dye. So things that travel far have strong solvent attractions, and things that fall out sooner have stronger paper or stationary phase attractions. And then the other thing that we can do with chromatography, you guys, is we can compare one dye to another. So like, let's say I did the chromatography at home with my black marker and Shreya did it with her black marker, and we both saw green. And it's like, oh, I wonder if those are the same green colored dyes. But maybe Shreya's paper was a lot bigger than my paper. So I can't say, oh, well, my green dye traveled 2 centimeters, and Shreya's is like, well, mine traveled 20 centimeters. That's not how we compare them. We don't compare them by distance traveled. We compare them by a proportion of distance traveled to the solvent front. So I would basically measure, and it's called a retention factor or an RF factor. I would calculate how far my green spot traveled versus how far in total my solvent front traveled. So I would do this distance divided by that distance. And Shreya would do the same thing with hers. And if we got the same RF factor, we know we had the same green colored dye. Okay, so that's chromatography. The other, sorry, my diagram on this one is so small. The other separation technique that the AP exam would expect you to know about is distillation. So this was chromatography. This other one is a diagram of distillation. And this separates things, not based on their attraction to a mobile solvent. This is separation based on boiling point. Differences in boiling point or volatility. Something that's very volatile will boil off first. Right?
Calling me out.
I didn't say anybody's name. So the first thing to boil off, so the first, we call these fractional distillations. So the first fraction is going to be the thing with the lowest boiling point. And then the last fraction is going to be the thing with the highest boiling point. So if you have a mixture of liquids and you want to separate out those liquids, you just start adding heat. And the most volatile thing, the thing with the highest vapor pressure and the lowest boiling point, is going to boil off first. And then here it'll come off down into this tube in the gas phase. This is a cooling tube. And it cools that gas and it'll condense back down into a liquid over here. And then we can change out that flask and we can put in a new fresh empty flask to collect the second fraction and then the third fraction for as many different things we have in the mixture. And the reason why we have a thermometer in there is so that we can see where the temperature flattens out. So like where that temperature flattens out is the phase change, and that's where we're collecting a fraction. We know that when that temperature flattens out, something is turning into a gas. That first fraction is turning into a gas. And then when we see that temperature start to rise again, that's when we know to switch out our flask to collect the next fraction that has a different boiling point. So lowest boiling point has the weakest IMFs. And the highest boiling point thing has the strongest IMF. Okay, let me pop up my chat here. Where is it? Where's my chat thing? Chat thing. there. IPS distillation, lots of glass broken. Oh, that's sad. I'm sorry. Okay, I'm not gonna look at this. You guys keep talking about all of the things you broke in IPS. All right, can you guys see hopefully my screen is back. Hopefully I'm still recording. Oh yes, good. It would be a real bummer to have to go re-record this whole thing. Okay, I've jumped all over the place. I think it's time to go talk about gases, you guys. Okay, so we talked about bond polarity, we talked about molecular polarity. We talked about IMFs and properties of IMFs. We talked about separation techniques. Oh my gosh, we've done such a good job. We talked about states of matter. We talked about our curves, blah, blah, blah. Okay, let's just talk about gases. Gases and we'll be done. No, gases and then a little bit of spectroscopy. Oh no, and solutions. Oh my God, this is a lot of stuff. I forgot how much was in this unit. Okay, I'm gonna talk fast. Here we go. Solutions. How do we get something to go into solution? Well, so if something is a solid, let's say it's an ionic solid, we've got a crystal lattice structure. So this is a solid. And we want to dissolve it in something. If this is a crystal lattice structure with charged particles, I'm going to want to dissolve it in something polar. Because remember the rule, how do we get things to dissolve? The solubility rule is like dissolves like. So if you want to dissolve something ionic or something polar, you want to dissolve it in something polar. So this thing will dissolve in that thing. A solid will dissolve in a liquid to make a solution. Now I've got my ions floating around in solution. So this is now aqueous. And the reason why this happens, like why would this solid dissolve in this liquid? Two reasons. One is if it's like dissolves like, you are going to have, oops, I didn't want to write it that way. You are going to have some solute, solvent interactions. There are going to be some new IMFs between the solute and the solvent. In this case, it would be ion dipole attractions, right? Remember, when you dissolve a salt in water, you will get ion dipole attractions. The other reason why solids dissolve in liquids is it increases entropy of the system. So that's a good thing too. So if this was ion dipole, you would want to make sure that you drew the oxygen portions of your waters being attracted to the positive cation in solution. And your negative, your larger negative anions would be surrounded by the partially positive, oops, oh gosh, that was a mistake. Your partially positive hydrogens. So make sure you guys can draw appropriate particle level diagrams for the solubility of both ionic compounds and covalent compounds. Like you can have covalent compounds dissolved in water, they just don't separate like this. The whole molecule will get surrounded. And of course, you know, so the reason why we're talking about this in this particular unit is because when I say like dissolves like, I'm talking about similar IMFs. Polar dissolves in polar, nonpolar dissolves in nonpolar. And we can measure the degree to which something dissolves with KSP, remember that, right? Our solubility equilibrium constant. That if we have big KSPs, it means something is really soluble. And if we have small KSPs, it means they are not very soluble. And the other way that we can talk about or quantify concentrations is with molarity, which is an actual measure of moles of solute dissolved per liter of solution. So KSP talks about like how soluble is something, like degree of solubility, and molarity measures actually in a particular solution how much stuff is dissolved. And the last thing I want to talk about here is how we can actually measure the concentration of a solution in the lab. And we did this in the lab. We used Beer's law. Remember this one? Where we measured concentration based on the absorbance, like how much light got absorbed by that solution. Okay, so this is Beer's law. And it relates concentration or molarity to absorbance. And A is a constant and B is the path length, like how far did that light travel through the solution. But we didn't even actually have to use the constant and the path length when we did this lab because we just made ourselves a calibration curve. Do you guys remember we looked at absorbance and concentration and we got a curve that related absorbance to concentration. So like when the absorbance of a colored solution went up, that was because its concentration was going up.
Wait, what was the curve called again?
It was called a calibration curve.
Oh, right. Okay, thank you.
Yeah. And now, of course, in order to do this, you guys, you have to have a colored solution. All right, so of colored solutions. Can't do it with colorless solutions. Right, so if I have this like colored solution here, and I pick a wavelength of light to pass through it, the machine can, the colorimeter can actually measure how much light gets transmitted. And the inverse of how much light gets transmitted is how much light got absorbed by the solution. So the darker in color this solution is, the more light gets absorbed. So we just pass different wavelengths of light through the solution, measure transmittance. The transmittance, the machine automatically inversed the transmittance into an absorbance value, and from the absorbance value, we would be able to calculate what the concentration of that solution was. Remember we did it with that purple colored solution in the crystal violet lab? Okay. Now, this whole thing about looking at how matter behaves in the presence of light, or how matter and light interact with each other, is called spectroscopy. And that's going to be the last thing that we talk about in today's lecture. But remember this when we get to that point, right? How light and matter interact with each other is spectroscopy. But before we do that, oh, it's 11:50. I'm supposed to let you guys go. If you want to go, you're free to go. Otherwise, I'm going to keep talking about gases. Is everybody okay? I hope we're okay. Let's talk gases and then we'll come back to that spectroscopy conversation. Okay, so gases. Gas behavior is governed by something that we call kinetic molecular theory. And kinetic molecular theory just basically says that gases are made up of particles that have mass. Particles with mass. Those particles are in motion. Kinetic, right? In motion. And we are going to assume that under ideal conditions, they have very few attractions and repulsions between those particles. In other words, gases are things with weak IMFs. And the last thing that we're going to talk about gases, or the last thing that sort of governs gas behavior, is the space between the particles is much greater than the size of the particles themselves. In other words, gases are compressible. There's a lot of space between those particles. So when we talk about the volume of a gas, we're not actually talking about the volumes of the particles themselves. When we talk about the volume of a gas, we're talking about the total volume occupied by that gas. So the reason why I would say that this is a 1 liter sample of a gas is because this container is 1 liter, not because these individual particle sizes add up to a liter. They definitely don't, right? And we can measure gas behavior or quantify gas behavior with a couple of key gas laws. Obviously, there's our ideal gas law. And we get all of our variable relationships from this as well. And the ideal gas law can obviously be manipulated and rearranged to look at changing sets of conditions. Remember the combined gas law? We can make predictions about what the pressures and temperatures will be if we mess with a set of conditions. We can calculate the total pressure of a mixture of gases by just adding them all up. This is Dalton's law of partial pressures. We can also calculate the individual partial pressure of a gas by multiplying the mole fraction of that gas in the mixture times the total. Right? So for example, like if this is a mixture and this has a bunch of blue gas in it, and I have just 2 molecules of red gas, this red gas is contributing way less to the pressure than the blue gas is. So the more moles of gas you have, the bigger contributor they are in terms of the partial pressure or the total pressure, both really. And then lastly, we can get the density of a gas by rearranging Pivnert. So the density of a gas, which is like moles over volume or mass over volume, is equal to N over V. Sorry, I know I did that wrong. I shouldn't try to derive things in my head. The pressure times the molar mass over RT. So like if I were to rearrange this equation and get moles over volume, that would result in P over RT. So there's my P over RT. But moles over volume is not, that's not how we measure density. We measure density in grams over volume, so I would have to multiply by my molar mass. And, lastly, and this will lead us into our next conversation, lastly is the speed of a gas. Okay, so when we think about gas movement will depend on 2 things. It'll depend on temperature and it'll depend on the mass of a gas. So like for example, we know that kinetic energy is equal to 1/2 mv squared. So when I'm talking about the speed that a gas is moving at, the velocity of a gas, the velocity depends on its mass and on its temperature, okay? And the equation for the root mean squared speed of a gas, and I'll talk root mean squared speed here in a second, is 3RT over molar mass. You don't need to memorize any of these equations, you guys. Right? You're going to either be able to look up the equations, you're going to have your equation sheet printed out and handy during the test. Okay? Now, the reason why we have this thing called root mean squared speed is when I have a sample of a gas, right? I've got like billions of particles of that gas. They're not all moving at the same speed, right? Some have collided and so have really low velocities, and some have just come off of a collision and have really high velocities. There's this distribution or range of speeds within a sample. And so that's what these diagrams below are showing us. These are called Maxwell-Boltzmann diagrams. Okay? And they show the distribution of particle speeds. So let's take a look at this green. Let's first look at this green room temperature gas, okay? This sample has, a certain number of molecules in it. And like I said, some are moving really slow, they're like over here, and some are moving really fast, they're like over here. But on average, like your most probable speed is at that peak. Like that's your most, sorry, that's not your average, that's your most probable. So speed most probable. That's the speed that most of your molecules are moving at. The speed in the kinetic energy equation, like when we say 1/2 mv squared, this speed relates to what we call the root mean squared speed. It's just a statistical speed, and it's not always the most probable, okay? So the root mean squared speed is probably going to be close to most probable, but maybe not exactly, okay? Now, if I were to take this gas, so this would be like my root mean squared speed. If I were to take this gas and I were to heat it up, right? If I were to increase my kinetic energy, that's going to increase the velocity, right? So if I look at this and I increase the kinetic energy, that's going to increase the velocity. This is, of course, if we're talking about the same gas, like let's say it's hydrogen for all three of these examples. That is going to increase my root mean squared speed. See how my peak has shifted over to the right? Now, of course, when we shift something, when we've got a wider variety of speeds that are possible, that flattens the curve. This is the whole thing about, like, Theo did a funny coronavirus post on the Hellhole page, right? About flattening the curve. So when we're talking about coronavirus, and the reason we're not in school right now is because this, with all of the social distancing factors, like, yes, hopefully fewer people get coronavirus, but even if we have the same number of people that get it in the end, as long as we slow down that time period, we increase that time period in which people get sick, that flattens that curve out. Like, so the number of people that end up in the hospital at any given time is going to be lower so that we don't exceed our medical system's capacity. So when you've got a wider variety of speeds available for that gas to move at, that peak is going to be lower because they're going to be spread out over a bigger distribution of speeds. So same thing with flattening a pandemic curve. Aren't you guys lucky to be living in such exciting times, right? So when we slow down the spread of the virus and we give it more time, just like with our gases, more possible speeds, that curve flattens out. Okay, so with an increase in kinetic energy, you're going to get an increase in velocity. And if we were to cool that gas and give it fewer possible speeds to distribute over, that peak gets higher. Okay, so like if everybody gets sick at the same time, you guys, that's how many people are going to end up in the hospital at the same time, and that's a problem. So for colder gases, your peak is going to be higher, but at a slower speed. So when we decrease kinetic energy, you're going to decrease the velocity that your gas is moving at. Now that's if you're talking about gases of the same mass. We have different Maxwell-Boltzmann diagrams if the gases have different masses. So here we're talking about gases all being at the same temperature, but gases of different masses. So if temperature is staying the same and you increase the mass of the gas, so instead of talking about hydrogen gas, which is really light, instead, let's look at oxygen gas, which is much heavier. We increase the mass, you're going to have to decrease the velocity at the same temperature. So if these are all at 25 degrees Celsius, hydrogen's actually going to move a lot faster at that temperature than oxygen because oxygen is heavier. So it's going to have a slower speed at that same temperature. Okay, that was a mouthful. And I started talking about coronavirus. Any questions on gas behavior and gas laws? No? I don't even know if you guys are still here. You guys could all be gone for all I know. I'm sitting here talking to myself. Last thing to talk about, spectroscopy. And my guess, you guys, is that whatever questions they ask you are going to be lab-based. They're going to have to be lab-based. You're going to have to analyze some sort of experiment because otherwise, you know, they're just going to be asking you things that you could go look up. So my guess is a lot of this is going to be experimental based. That's why I'm spending time talking about like chromatography and distillation and spectroscopy. So this is a general term that we use. Spectroscopy is looking at how matter and light interact with one another. So like one example is like when we use those colorimeters, right, to measure how much light gets absorbed by a colored solution. So we just like pass a wavelength of light through here, like we were saying, and we can measure absorbance and concentration. That's one way that you can use light to help you better understand the behavior of matter. Another example of spectroscopy is like in the flame test lab. So like here's our Bunsen burner. Here's our Bunsen burner flame. And we take a Q-tip of sodium chloride and we put it in there and all of a sudden our flame goes yellow. And so like why are we seeing yellow light when sodium is heated. Okay, so these are called flame tests. And we know that we see those different colors of light because of electron transitions, right? When we see an electron jump in energy level, you know, from the N1 up to the N2 and then fall back down, and we get certain wavelengths of light. So this is another example of how light and matter interact and tell us something about that substance. We could also look at the color of light through a spectroscope, and you would see, you know, very distinct wavelengths of light being emitted. So for example, for sodium, you would get a lot of, you know, yellow. You'd probably get a lot of yellow and orange lines, you know, maybe a green line in there somewhere. These, when you look at this light through a spectroscope and you see all of the distinct colors of light, these are called atomic emission spectra. And remember, those are like a fingerprint for the substance. And we can actually calculate how much energy is being transmitted, or emitted, I should say, using our Planck's constant equation. And we can also calculate the wavelength of light using our speed of light equation. And so those are the three examples that you guys are probably the most familiar with. And I doubt that this next part is going to be important, but I'm going to throw it in there anyway, because sometimes, you know, I was looking through one of these AP exam review books, and one of the pieces of information that they wanted you to know is this. Now, this looks like a lot. It looks a little confusing. Don't worry about it. Okay. This is a chart that talks about the different frequencies or wavelengths of light and what kinds of transitions they relate to in terms of the matter's behavior. Okay, a bunch of people left. Bye, bye, bye. People are molecules. Speed is amount of coronavirus. This is overwhelming. I'm sorry. Oh no. Okay, I should have been looking at the chat. I'm sorry, you guys. Don't be overwhelmed. All right, here we go. This is the last little piece. And it's not actually anything new. Okay, what this chart is telling you is that when we get emissions of light that are around 200 to 800 nanometers in wavelength, like when we see these wavelengths of light being emitted, that means that you are seeing an energy change in the terms of where the valence electrons are in the atom, like just like that Bohr model that I was just diagramming. Okay, so like if you get emissions that are in that sort of UV or vis range of the electromagnetic spectrum, what you're seeing are electrons transitioning between energy levels. Okay. If you, oh, it says my connection is unstable. Shoot. I'm going to wait a second. Can you guys hear me? Is anybody there? Lindsay, can you hear me?
Yeah.
Okay, thank you.
You're
Okay,
good.
okay.
You
All
like
right.
stalled for a minute, but you're good now.
Okay. Okay. So, so if what we're seeing is visible light or UV light, that means that the energy transition that's happening is between electrons and their energy levels. If the transition is in the infrared range, oh, these are the different devices. Ignore this column. That's just the different names of the different devices. So if you get visible or UV emissions, we're talking about electrons changing energy levels. If what we're seeing is infrared transitions, that means that the molecules have changed their vibrational frequency. Remember, we talk about motion of particles in different ways. Motion of particles, when we were talking about microstates, they can vibrate or they can rotate. So if we're seeing infrared transitions, that corresponds to a change in the vibrational energy as opposed to a change in electrons' energy level. And if the emissions are in the microwave portion of the electromagnetic spectrum, we have changed the rotational energy of the substance. I don't know why that one little stupid piece of information is like in all of these AP review books, but if you see something talking about electromagnetic spectrum and, you know, electron transitions or vibrational transitions or rotational transmissions, and these were the only three that are in that review book, just refer back to this slide. Well, I guess it's not a slide, but maybe just put that one little piece right there in your notes. Okay, and you guys are obviously most familiar with these transitions in electron energy levels. Those are the ones that we actually saw and worked with in the lab. We don't have the capacity. We don't have like an IR and NMR. We don't have these types of devices. So I don't know why they expected us to talk about them. But there it is. And you know what you should know. I mean, just like what you really should know, and I guess this should have been what if I was in charge of the AP exam, this is what I would care about. I would just care about the fact that you guys know that the electromagnetic spectrum is a wide range. Like when we talk about, you know, things traveling at the speed of light, there's a lot of different things that travel at the speed of light. You know, on the low end of your spectrum, you've got like radio waves and microwaves. And then, you know, some IR. And then like, here's your visible range of your spectrum. And then you've got UV. And then you've got, what's in between UV and gamma? I don't remember. Something else, higher energy. Oh, X-ray, there we go, duh, X-rays. Okay, so like down here, this is your high energy end of your spectrum. This is where you have short wavelengths and high frequency. And down here is your low energy end of your spectrum, where you have long wavelengths and you have low frequency. And your visible light, of course, you know, is a range of colors, your Roy G. Biv. You know, so your red light is your lower energy light and your violet light is your higher energy light. So all of this spectroscopy chart was saying, you guys, is that if you were to be visualizing things within, you know, this range of the spectrum, then you're probably seeing electrons changing energy levels. And if you're seeing, see, I don't even have it memorized. If you're seeing just IR, then you're probably seeing changes in vibrational energies of the molecules. And if you're seeing microwave emissions, then you're probably seeing rotational changes in motion of the particles or energy of the particles. Okay. I think that's it. I'm going to stop.